The first thing that we want to look at on this section is what is referred to as differential operators. So in the past, when we looked at things like y prime, by that we mean the derivative of y with respect to a particular variable, or we could call that dt of the variable y. So in this case, we're going to introduce some new notation where instead of calling that the derivative with respect to t of y, or calling it y prime, we call it d of y, meaning the derivative of y. Likewise, the second derivative is the derivative of the derivative of y, and we're going to denote that d squared y. So this just means the second derivative of y, which is really a composition of d. It's the derivative of the derivative of the function y. So while it looks like a power, it's really a composition here. So we want to look at some properties of these. Let's start out by looking at an example, and let's show that this is the same thing as d squared plus 3d plus 2 on the function of y. So the way we're going to show that is we're going to do it each way. If we do this operation on y, then we're going to do this operation on y. So that's like our inside operation, and then we're going to apply this operation to that result. So our inside operation, we're taking the derivative of y, so y prime, 1 times y, so y. And then to that, we want to do these operations. We want to do the operation, the derivative of that, and then the operation 2 times that. We take the derivative of that, we get the second derivative of y plus the first derivative of y. And then if we do 2 times that, we get 2 times y prime and 2 times the function y. If we combine like terms, we have the second derivative once, we have 3 times the first derivative, and we have twice the function. And if you look, that's exactly what this is. If we take d squared plus 3d plus 2 and do that operation on the function y, then we're taking the second derivative of y, we're taking the derivative of y and multiplying it times 3, and then we're doubling the function y. So those are the same. So it would seem to indicate that any time we have a polynomial or have something of this nature, that these two are always the same. But it's going to turn out these are the same as long as our coefficients of d, as long as our coefficients are constants. If we introduce coefficients that are not constants, then we run into some problems. So let's look at an example of that. Let's look at the example d of 2d plus what I want, 4t. And let's show that that is not the same as 2d plus 4t times d. So let's do it the right way first. I say the right way. Decide like what's on the right first. So if we apply that operator to the function y, then we do this one first. So we take the derivative of y, which is y prime. And then we do this operation on y prime. So if we do this operation on y prime, we take the derivative of y prime, which is y double prime, and we multiply it times 2. And then we take 4 times t and multiply that times y prime. So that's what we get when we do that operation on y. But if we do the operation this way, 2d plus 4t, and we do that operation on y, then we're doing that operation first, derivative of y times 2, and then we're doing 4 times t times the function y. And then the next operation is that. So for the first term, to take the derivative of it is the derivative of y prime, which is y double prime, times 2. But when we take the derivative here, we have a problem. T is a variable and y is a variable, so we have to use the product rule to take this derivative. So the product rule says take the derivative of the first part, so the derivative of 4t is 4 times the second part, plus the first part times the derivative of the second part. So notice those two things don't match. So if we have coefficients or other functions other than y in our operators, then these things don't have linear properties. So we do have to be careful there. But as long as our coefficients are constants, then we can simplify our notation using this differential operator notation, and it's going to make it easier to solve various systems of equations. In 5.1, we looked at having a system of differential equations where we had x prime, x, y prime, y, and then possibly some other terms, and we had to solve that system, and that notation could get a little bit messy. But here, by using this differential operator notation, it can make some of these a little simpler. So let's work through the system. X prime equals x minus y, and y prime equals y minus 4x. So we want to begin by getting our x's and y's on one side. So for the top one, we're going to rewrite that x prime minus x plus y equals 0. And for the second one, y prime minus y plus 4x equals 0. So in terms of our variable x, our operators are that we have the derivative of x, and we're subtracting 1 times x. And for our variable y, we just have 1 times that function. For the second equation, for our variable x, we just have 4 times that variable. And for our variable y, our operation is we have our derivative of y, and then we're subtracting 1 times our function. Now I made this a little messier than it had to be by mixing up parentheses and brackets. It's kind of standard to put brackets around your variable that's your function, and put parentheses around the operator. So parentheses, parentheses, bracket, bracket. So since our operators behave linearly when our coefficients don't have variables in them, then we just solve this like a system of linear, a linear system of equations. Here our variables are x and y. So we could do this several different ways. To eliminate x, we could multiply the top equation by -4, and we could multiply the bottom equation by d minus 1. So if we do that, the top equation is going to be -4 times d minus 1 times x, and then distribute that, so -4 times y equals 0. The bottom equation is going to be 4 times d minus 1 x, d minus 1 times d minus 1, So that's going to be d minus 1 squared, that's on y, equals 0. So these are opposites, so those cancel. So we get d minus 1 squared. Well, if we multiply that out, that's d squared minus 2d plus 1. And if we're combining with that, then that's minus 4. And that's our operative for y. And that's a 0 on the other side. So if we combine those, our operative for y is d squared minus 2d minus 3. And that's our operation on y. So we can rewrite that as y double prime minus 2y prime minus 3y equals 0. And that's just a homogeneous second order differential equation with constant coefficients. So if we write our characteristic equation, we would end up with r minus 3 times r plus 1 equals 0. So r is 3, r is negative 1. So y would be c1 e to the 3t plus c2 e to the minus t. So that would give us y. Now that we have y, we need to get x. And we can do this several different ways. We could go back to our system of equations at the top, and we could, instead of eliminating x, eliminate y, and that would give us an equation with operators on x, and then we could solve that differential equation. Or another thing we could do is we could take our system of differential equations. We could solve one of these equations for x in terms of y. Notice the bottom one has x and then y prime and y. So we have y prime equals y minus x. If we solve that for x, we get y prime minus y equals negative 4x. If we divide both sides by negative 4, or we could multiply the left side by negative 1/4, and that would give us the same thing, then x is just going to be negative 1/4 times y prime minus y. So since we know what y is, we can put y in. Since we know what y prime is, we can, or since we know y, we can get y prime. And we can plug that in, and that'll give us a function for x. So y prime, if we take the derivative, it's 3c1 e to the 3t minus c2 e to the negative t. So then x is going to be negative 1/4 y prime, so 3c1 e to the 3t minus c2 e to the minus t minus y. So minus c1 e to the 3t plus c2 e to the minus t. So we can simplify that a little bit. So on the inside, we have a 3c1 and a minus c1. So that's 3 minus 1 is 2 c1 e to the 3t. We have a minus c2, and when we distribute that negative, we have another minus c2, so minus 2 c2 e to the minus t. So that gives us a solution for x. So let's just copy y down. So y is c1 e to the 3t, c2 e to the minus t, and x is that. So if we were given some values, we could solve and we could find out what c1 and what c2 needed to be for our particular problem. If we did it the first method we described, which would be to eliminate y instead of x, eliminate y and then solve that differential equation for x, then when we get to the point here of writing x in terms of constants in our e's, we're going to have the same exponentials. We're going to have e to the 3t and e to the minus t, but we don't necessarily have the same coefficients. Notice the coefficient of e to the 3t for x is negative 1/2 if we multiply those two. So negative 1/2 of c1. If we multiply those two together, it's positive half of c2. So this c2, and here we have half of that c2. So these coefficients are not exactly the same values. So if we did it the other way, we might have k1 and k2, and then we would need to find out how are these coefficients and these coefficients related. So we don't want to have C1, C2, K1, K2. We would be better off having one set, either having just C1 and C2. And the easiest way to do that is like we did here. After we get one solution, then use our differential system to solve for the other variable that we need the solution for, substitute in our derivative and our function, and that allows us to find, in terms of the same constants, what the solution for x is. So let's make a quick note. So let's generalize this, that when we have L1, and L1 is just an operator or a list of operators on a function x, or on our variable x. And L2 is a polynomial of operators involving d on y. So for example, it could be d plus 2 is the operator on x, and d minus 1 is the operator on y. So L1 and L2 are just the operators on each of these. So that equals, let's call it F1, and then L3 on x and L4 on y equals F2. So we could solve for x and y by using Cramer's rule. If we list our determinants, L1, L2, L3, L4, general determinant, so L1 times L4 minus L2 times L3. And then to get x, so dx, if we replace that with F1, F2, then F1, F2, L2, L4, then that determinant would be, turn my magic pen off. F1, F2, L2, L4. So that would be the operation L4 on F1 minus the operation L2 on F2. And then dy will replace the second column with F1 and F2. So that would be L1 on F2 minus L2 on F1. So x is just dx over d, and y is dy over d. So nothing new there. So where we end up not getting solutions, or getting what we refer to as degenerate solutions, if our solution degenerates, we can't divide by 0. So if d equals 0, and we have to be careful, maybe I should use different letters here. D here means the determinant. So if L1 times L4 minus L2 times L3, if those operators, if these operators times those operators minus these operators times those operators equals 0, then our solution degenerates. So it could be that there's no solution, or it could be that we have a solution with a vast number of arbitrary constants. Now, if that determinant is not 0, then we should get a solution here and solution there. And notice those are going to be they may have functions over here. In the example we did a minute ago, we had zeros on the right side. It was homogeneous. But it could be that it's not homogeneous, so we have to get our general solution by getting both our homogeneous and our particular solutions when we solve for x and we solve for y. All right, so let's work through an initial value problem. Let's take a look at this one. dx dt equals 2x plus y minus e to the 2t, where x of 0 equals 1, and dy dt equals x plus 2y, where y of 0 equals negative 1. So let's take a look at this example. So, excuse me. So let's convert the top equation into differential notation, and also let's get everything to the left side that is either an x or a y. So dx dt is the derivative of x. If we move that to the left side, then we have a minus 2x. If we move that to the left side, we have a minus y. And then on the right side, we have minus e to the 2t. So the middle term is in terms of x. The first term is in terms of x. So if we bring out the x, we have the derivative of x, and we have twice x. So if you want to think about it as factoring out an x, then that's what you have being done to x, the derivative of x and minus twice the function x. And then for our function y, we just have it subtracted one time. And that equals minus e to the 2t. So for the second one, so that's our first equation. For the second one, we have the derivative of y. If we subtract that from both sides, we have minus x. Subtract that from both sides, we have minus 2y equals 0. So our operators on y is we're multiplying y by a constant, and we're also taking the derivative of y. So on y, we have its differential minus twice y. For x is being multiplied times the minus 1. So on the right side, we have 0. So if we rewrite this, just bring them together, we have for x, for the first one, we have the differential minus 2. That's what's being done to x. And then we have a minus 1. That's what's being done to y, equals minus e to the 2t. For the second one, we have a minus 1. That's what's being done to x, plus d minus 2. That's what's being done to y, equals 0. So let's solve this system of equations. We can get rid of either variable we want. Let's just get rid of x. So if we multiply the first equation, the second equation by d minus 2, then the top equation has positive d minus 2 of x minus y, or 1y, equals minus e to the 2t. The second equation, we're going to have a minus 1 times d minus 2, or we could call that minus, times d minus 2. That's what's being done to x. And then plus, if we do that, and that times that one, we're going to have d minus 2 squared. That's what's being done to y. And when we do that times the right side, we get 0. So when we combine these, the combined operators on x cancel. We have a d minus 2 operating on x, a minus that operating on x, so those undo each other. So we have a minus 1 operating on y. If we square that binomial, we have d squared minus, we have their product, the minus 2d twice, so minus 4d. And then the second one squared, that's plus 4. So that's also being done to y. If we add the right sides together, we have minus e to the 2t. So if we combine our operations on y, we have a d squared, we have a minus 4d, we have a 4 minus 1, so that's a plus 3, and on the other side, minus e to the 2t. So if we put this in the standard form, we have the second derivative of y minus 4 times the derivative of y, and then 3 times y. And that equals minus e to the 2t. Now, remember, to solve this, we have a homogeneous solution and a particular solution. So for the homogeneous, the characteristic or auxiliary equation is r squared minus 4r plus 3 equals 0. If we factor that, we get r minus 3 times r minus 1. So for r, we get r is 3 and r is 1. So our homogeneous solution is c1 e to the 3t plus c2 e to the 1t. So that's our homogeneous. Now we need our particular solution. Notice e to the 2t was not part of our homogeneous. So that means the form of our particular solution is going to be a e to the 2t. We just need to find out what coefficient does e to the 2t need such that this function is a solution to that differential equation. So we need the first derivative of y. So the derivative of the exponent is 2, so 2a e to the 2t. We take our second derivative. Again, the derivative of the exponent is 2, so we get 4a e to the 2t. So if we substitute that into our differential equation, we have our second derivative, 4a e to the 2t, minus 4 times our first derivative, so 4 times 2 is 8, a e to the 2t, plus 3 times our guess. So our guess is this, so 3 times that. And that needs to equal minus e to the 2t. So if we combine like terms on the left side, all of these are e to the 2t's. So we have 4a minus 8a, that's minus 4a plus 3a, so minus 1a equals minus e to the 2t. So in order for these two to match, our coefficients have to match, so minus a has to equal negative 1, thus a is 1. So our particular solution is 1 e to the 2t. So if we combine our homogeneous and our particular solution, then we have c1 e to the 3t plus c2 e to the t plus 1 e to the 2t. Our particular solution was that, so this is our homogeneous, that's our particular. So that's what we get for y. Now we need to go back and get x. So in this bottom equation, notice we can solve it for x pretty easily. If we subtract 2y from both sides, we get x equals dy dt minus 2y. Sure, I remember that correctly. Yeah, if we subtract 2y from both sides, we have y prime minus 2y equals x. So x, again, is y prime minus 2y. We know, in general, what the solution for y is. So we need y prime. So the derivative of this is 3 e to the 3t, so times c1. The derivative of this power is 1, so we get c2 e to the t is the derivative of the middle term. And the derivative of the last term is 2 e to the 2t. So x is the first derivative, 3c1 e to the 3t, plus C2 e to the t plus 2e to the 2t minus twice y. This was y. So if we do twice this, let's just do this. So minus 2 times bring down y. So if we combine like terms, we have a 3c1 e to the 3t. When we distribute, that's going to be a minus 2c1 e to the 3t. So 3c1 minus 2c1 is 1c1 e to the 3t. Then for our e to the t's, we have a c2 e to the t. When we distribute there, we have minus 2 c2 e to the t. So 1 minus 2 would be minus 1 c2 e to the t. And then when we distribute to there, we have minus 2 e to the 2t plus 2 e to the 2t, and those cancel. So that gives us x. X. And we have y. So those are our general solutions, but we don't have our C1s and our C2s yet. So if we recall, for this particular problem, in the equation x, when t is 0, x is 1. In the equation y, when t is 0, y is negative 1. Make sure that I wrote the problem down correctly. Yes, that's correct. So we need to substitute these in. So the top equation, when we put a 0 for t, we get an exponent of 0. E to the 0 is 1. Same thing here. E to the 0 is 1. So we're going to get C1 minus C2 equals 1. Because when we plug a 0 into this, our answer should be 1. For the second equation, when we plug a 0 in, our answer should be negative 1. So our answer should be negative 1 when we plug a 0 in for t. So e to the 0 is 1, so we get C1. E to the 0 is 1, so we get C2. E to the 0 is 1. If we subtract 1 from both sides, then that bottom equation equals C1 plus C2. Remember, our top equation is 1 equals C1 minus C2. So if we add the equations together, the C2's cancel. So we get 2 C1s equals negative 1. So thus C1 is negative 1/2, dividing both sides by 2. So now we can solve for C2. So let's just take the top equation, and where we have a C1, put in a negative 1/2. If we add 1/2 to both sides, we have negative 2 plus 1/2 equals C2. We need a common denominator, so this is going to become 4 over 2 plus 1/2. So negative 4 plus 1, C2 is negative 3/2. So that gives us our two solutions. X, let's bring this down. X is C1 e to the 3t minus C2. C2 is negative, so minus negative 3/2 e to the t. So that's, we put a C1 in, we put a C2 in. So that means x is negative 1/2 e to the 3t plus 3/2 e to the t. So that's our solution for x. For y, y is C1 e to the 3t plus C2 e to the t plus e to the 2t. So that makes y come out to be negative 1/2 e to the 3t minus 3/2 e to the t plus e to the 2t. So given that system of differential equations and those initial values, we were able to find x and we were able to find y.